but differ in their spatial arrangement of groups or atoms in molecule is called stereoisomers. Isomers having same bonding connectivity. So stereoisomers, isomers having same bonding connectivity but differ in spatial arrangement of groups or atoms in molecule is stereoisomers. Stereoisomers are two types. Generally, stereoisomers are two types. One is enantiomers. Second one is diastereomers. So every enantiomer is chiral and optically active. Every enantiomer is chiral and optically active. Diastereomers, again here, some diastereomers are chiral diastereomers, some diastereomers are achiral diastereomers. So example for chiral diastereomers is meso and active compounds, and achiral diastereomers example is cis and trans compounds are the example for achiral diastereomers. That means diastereomers, some diastereomers may chiral or may not achiral. So some diastereomers are chiral and some diastereomers are achiral. But every enantiomer is chiral, optically active. This is it. Next is stereo selectivity. Stereoselectivity. Any chemical reaction which produces unequal amount of stereoisomers or exclusively one stereoisomer, then that reaction is called stereoselectivity reaction. Okay, when reactant in reacting with reagents, solvent, catalyst, and then produces stereoisomers, isomer 1, stereoisomer 2. If this one is one stereoisomer is major, one is another one is minor. That is the stereoselectivity reaction. That means any chemical reaction which produces unequal amount of stereoisomers or exclusively one stereoisomer, then that reaction is called stereoselective reactions. That means these stereoisomers may be chiral, enantiomers or diastereomers. That means the stereoisomers are maybe chiral or chiral. General example I am given here. I am taken this 2-butane. When this 2-butane reacting with the sodium, liquid ammonia, ethanol, then produces trans 2-butene and cis 2-butene. This trans 2-butene is the major and cis 2-butene is the minor. This is the best example for stereoselective reaction. These are the diastereomers, therefore diastereoselective reaction. These are the diastereoselective reaction. That means these are the stereoselective reaction. The products are achiral stereoisomers. When another example I am taken here, when Baker's yeast is a reagent, when I am taking is 2-butanol, when this 2-butanol reactant with Baker's yeast, then produces 2 isomers, OH, hydrogen attack from top side, S, this is major. When hydrogen attack from downside, it is a minor. These are the chiral stereoisomers. Unequal amount of chiral stereoisomers are produced in this reaction. Therefore, this reaction is a stereoselective reaction. Okay, this is a enantioselective reaction. Selective reaction. This is when I am taking next one is very important from here. Asymmetric synthesis. Definition I am giving you. Asymmetric synthesis. asymmetric synthesis. Any chemical reaction which produces unequal amount of chiral stereoisomers or exclusively one chiral stereoisomer, then that reaction is called asymmetric synthesis. That means when reaction, any one of reactants in presence of reagents, solvent, catalyst, then produces chiral stereoisomers. Chiral stereoisomer 1, then produces chiral stereoisomer 2. This is chiral stereoisomer 1 is major, another one is minor. This is the this is the asymmetric synthesis. That means any chemical reaction which produces unequal amount of chiral stereoisomers or exclusively one chiral stereoisomer, then that reaction is called asymmetric synthesis. So here I am taken here. When comparing these two examples, when we comparing these two examples, here that when first reaction, these two are not a chiral products, therefore it is not a asymmetric synthesis. Not a asymmetric synthesis. Not a asymmetric synthesis. It is only stereoselective synthesis. When compared to this example, here the products are chiral stereoisomers. Here the products are chiral stereoisomers. Therefore, it is a asymmetric synthesis and as well as stereoselective synthesis. Okay, that means any chemical reaction which produces unequal amount of chiral stereoisomers, then that reaction is called asymmetric synthesis. Any chemical reaction which produces unequal amount of stereoisomers, that is a stereoselective reaction. Okay, all asymmetric reactions are stereoselective reaction, but all stereoselective reactions are not asymmetric synthesis. So next general principles for asymmetric synthesis. Next one is general principles for asymmetric synthesis. Next one is general principles for asymmetric synthesis. One is, in a reaction, if all the starting materials, that means substrate, reagent, catalyst, solvent, and auxiliary are achiral, then that reaction produces unequal equal amount of stereoisomer. That means that reaction is not a asymmetric synthesis. If any chemical reaction in the starting materials, any one of the starting material is chiral, then that reaction is became a asymmetric synthesis. Here, what is the general principles for principle for asymmetric synthesis means the starting materials. Here, these are the starting materials. So reactants, reagent, solvent, catalyst, and auxiliary. Any one of the, if all the starting materials, first point is, if all the starting materials are achiral, then that reaction is not a asymmetric synthesis. It is only stereoselective synthesis. If any one of the starting material, is chiral, then that reaction is become a asymmetric synthesis. Here I am seeing these two examples. In this first example, here the starting materials are the two-butane, sodium, liquid ammonia, ethanol. Here there is no any one of chiral starting material. Here there is no chiral starting materials. Therefore, this reaction is not a asymmetric synthesis. In the second example, here in this second example, that starting material, one of the starting material, this is Baker's yeast, is an enzyme. All enzymes are considered as a chiral substance. Therefore, it is a chiral. Therefore, this reaction became a asymmetric synthesis. That means if all the starting materials are achiral, that reaction is an only stereoselective reaction, not a asymmetric reaction. If any one of the starting material is a chiral, then that reaction became a asymmetric synthesis. Here, in this first example, in the starting materials are there is no one is a chiral, therefore that reaction is a stereoselective reaction. In the second example, that one of the starting material, that is Baker's yeast, the enzyme, all enzymes as considered as a chiral, therefore this reaction became a asymmetric synthesis. Next one is tropicity. Tropicity in molecule. Next one is tropicity in molecule. The definition for tropicity is stereochemical relationship between selected subunits of molecules is a tropicity. Stereochemical relationship between selected subunit of molecules is a tropicity. That is a subunits here. Subunits are ligands and phases. Here ligand means, again ligands means atoms and groups. Atoms and groups are the ligands. That means subunits are ligands and phases. Ligand means atoms and groups. Phases means double bond phase. That's up, down phase and up phase. Bottom phase and up phase are the phases. Here possible stereochemical relationships are three types: homomeric, enantiomeric, and diastereomeric relationships. Homomeric, enantiomeric, and diastereomeric. Next one is homomorphic units. Homomorphic units. So the selected subunit of molecules after hypothetical detachment from molecule, if structurally and configurationally same, then the subunits are called homomorphic units. Okay, I am taken here an example. Methane I am taken here. Here that means the selected subunits of molecule. I am taken these two are the subunits. The selected subunits of molecule I am selected these two. The selected subunit of molecule after hypothetical detachment from molecule. When we remove this from molecule, I am remove this. When we hypothetical detachment from molecule, if these are structurally and configurational same, that subunits are called homomorphic units. Okay, these two are structurally and configuration same, therefore these two are the homomorphic units. Another one is another example here. I am taken here two phenyl groups subunits. I am taken these two subunits. These two phenyl groups I'm detachment from molecule hypothetically, and these two are that structurally and configuration same, then these two subunits are homomorphic units. Okay, these are the homomorphic units. Definition is selected subunits of molecule after hypothetical detachment from molecule. If if that structurally and configurationally same, then the subunits are called homomorphic units. Next one is so homomorphic units are classified into classification of homomorphic units. So homomorphic units are classified into homotopic units and heterotopic units based on relationship with the rest of the molecule. If that homomorphic units are identical, then that is called homotopic units. If differ, then heterotopic units. Then homotopic units are again classified into homotopic ligands and homotopic phases. And heterotopic units are classified into stereoheterotopic units and structural heterotopic units. The stereoheterotopic units are again enantiotopic units and diastereotopics. These enantiotopic units are classified into enantiotopic ligands and enantiotopic phases. Diastereotopic units are classified into diastereotopic ligands and diastereotopic phases. That means we are studying these six. One is homotopic ligands and homotopic phases, enantiotopic ligands and enantiotopic phases, diastereotopic ligands and diastereotopic phases. That is covered in this classification of homomorphic units. First, we are discussing homotopic ligands.
Hello, sir, you are not audible.
Murthy garu, please wait 1 minute.
Okay, sir. Okay. Thank you, sir.
So here, so next one is homotopic ligands. I'm explaining here homotopic ligands. The following criteria is decided whether the homotopic ligands are homomorphic or not. Okay. First one is symmetry criteria. Based on two criteria, the selected subunit of molecules are we are decided that is a homotopic or not. First we have taken first criteria is symmetry criteria. That the selected subunit of molecules, that means homomorphic units, are interchangeable with CN symmetry. Interchangeable with the CN symmetry, then that subunits are come under the homotopic ligands. I am taken here one example: hydrogen, hydrogen, hydrogen. So that is a chloroform. Example is chloroform. In this chloroform, these three hydrogens I am selected. That is a homotopic ligands. This homomorphic ligands. These homomorphic ligands are interchangeable with C3 symmetry. These homomorphic ligands are interchangeable with C3 symmetry. Therefore, these three hydrogens are homotopic ligands. That means the selected subunit of molecules are interchangeable with CN symmetry, then that are come under the homotopic ligands. So this is one example. Another example is I am taken. So I am taken all these four hydrogens. These four hydrogens are interchangeable with the C2 symmetry like this and interchangeable with C2 symmetry like this. Therefore, these all hydrogens are come under the homotopic ligands. Next one is substitution criteria. Next one is substitution criteria. That hypothetical substitution of either ligand on one at a time by other ligand, then that is if the resulting products are homomers, then that subunits are called homotopic ligands. Same I am taken here. Again I am taken is a chloroform. When this chloroform, one hydrogen, two hydrogen, three hydrogen, H1 is replaced by bromine. H1 is replaced by bromine. H, chlorine, hydrogen, bromine. And H2 is replaced by bromine, chlorine, bromine, hydrogen, hydrogen. H3 is replaced by bromine, H, bromine. These are that homomers. These three are homomers. Therefore, these selected subunits of molecules are homotopic ligands. Next one is homotopic phases.
Sir, it is CHCl3 కదా సార్ క్లోరోఫార్మ్
CHCl3.
అవును
Okay.
సార్.
Okay.
మూడు మీరు హైడ్రోజన్ పెడుతున్నారు కదా.
Okay, just you take instead of hydrogen.
Okay, అది మార్చుకోవాలి సార్.
మార్చుకో. Otherwise you take chloromethane.
Sir.
Methyl chloride.
Sir.
So just we take either chloroform or methyl chloride.
Okay, sir.
Whatever that means, here at the carbon atom, three groups are same, one group is differ.
Sir.
Next, homotopic phases. Homotopic phases. That means based on two criteria, we are the selected phases are either homotopic or not. We are decided. First one is addition criteria. First one is addition criteria. So hypothetical addition of on either phase of one at a time. If the at ligands, if the resulting products are homomers, then that is phases are come under the homotopic phases. I am taken here. I have taken this formaldehyde. I am taking this formaldehyde. When this formaldehyde undergo addition reaction with methyl magnesium bromide, undergo addition reaction with methyl magnesium bromide from top side, from top phase, then hydrogen, and OH going to up downside and methyl coming to upside. Okay, if this methyl magnesium bromide approaches from back phase, then OH command to upside and methyl going to backside. Okay, these two are I am writing here in Fisher projection formula. So it is methyl come to left and OH going to right, and here also then hydrogen, and here OH coming to left and methyl going to right side. These two are homomers. So homomers means superimposable mirror images. Superimposable mirror images are called homomers. These two are homomers. Therefore, the selected phases, a double bond, one is up phase, down phase is there. Therefore, this phase up phase and down phase are called homotopic phases. Next one is symmetry criteria. The selected subunit of the selected phases are interchangeable with CN symmetry, then that phases are come under the homotopic phases. Here also same I am taken formaldehyde. So these are interchangeable with C2 symmetry. When we rotated, I'm H and H2, I'm labeling for your easy convention. Undergo C2 rotation, 180 degrees rotation, then H2 and H1. And this. So both phases are same, the molecule is same, therefore phase 1 down phase and phase 2 up phase are the homotopic phases. Next one is enantiotopic ligands. Enantiotopic ligands. Again, based on the two types. One is so based on two criteria, we can decide that ligands are enantiotopic or not. One is substitution criteria. One is substitution criteria. So that means I am taking one molecule. I'm H1, H2 labeling here, H1, H2. That means the selected subunit of molecules are substituted with a different ligands. Then resulting products are enantiomers. Then that subunits are come under that homotopic ligands. Here I am these two, H1 and H2 are the homotopic ligands. These homotopic ligands are substituted. Here H2 is substitution with the bromine, OH,
రావట్లేదు రాజు వైఫై ఆన్ చేస్తే ఫ్లైట్ మోడ్ ఆన్ చేస్తే వస్తలేదు. HBr and substitution with bromine. Bromine hydrogen. So these two are okay. I'm kept here. These two are non-superimposable mirror images. That means enantiomers. Therefore, the selected subunit of molecules are enantiotropic ligands. Okay. That means the selected subunit of molecules are substitution with the different group. Then the resulting products are enantiomers. Then subunits are come under the enantiotropic ligands. Next one is the substitution criteria. Second one is symmetry criteria. Next one is symmetry criteria. Okay. So the selected subunit of molecules are interchangeable with the second kind of symmetry elements. There is plane of symmetry, center of symmetry, improper my favorite flight. Yeah. Benzene. BNZ. Symmetric criteria. The selected homomorphic ligands which are interchangeable with second kind of symmetry elements. There is a plane of symmetry, in center of symmetry, improper axis of symmetry. Then that ligand homomorphic ligands are come under the enantiotropic ligands. Here I am taking another example. Same example I am taken here. Propanoic acid. Correct. Propanoic acid.
Okay. Class. Here, these two are the selected homomorphic ligands. These homomorphic ligands are interchangeable with plane of symmetry. Interchangeable with plane of symmetry. Therefore, these two ligands are come under the enantiotropic ligands. So another example. This is one example. Next one is dash stereotopic. Next one dash stereotopic. Next one is enantiotropic phases. Next one is enantiotropic phases. Again, first one is addition criteria. Addition criteria. The selected homomorphic phases under addition after addition resulting products are enantiomers. Then that phases are enantiotopic phases. I'm taken here one of the compound here. This compound phase 1 and phase up phase and down phase, and when undergo addition reaction with lithium aluminum hydride. These are from F1 side, bromine, chlorine, hydrogen, OH. From F2 side, chlorine, and here OH, hydrogen. So these two are that enantiomers. Therefore, that phase 1, F1, F2 phases are enantiotopic phases. Next one is addition criteria. Next one is symmetry criteria. In the symmetry criteria, same. The selected phases are interchangeable with the plane of symmetry, center of symmetry, and improper axis of symmetry. Then that phases are enantiotopic phases. So I am taking here one molecule, acetaldehyde. Acetaldehyde. This acetaldehyde, plane of symmetry, according to plane of symmetry, these phases are interchangeable. Therefore, these phases are enantiotopic phases. Next one is diastereotopic phases. Next one, diastereotopic ligands. Diastereotopic ligands. One is symmetry criteria. Symmetry criteria. The homomorphic ligands are not related with any kind of symmetry elements. Then that is called diastereotopic ligands. Not related with the CN and improper axis of symmetry. Okay. The selected homomorphic ligands are which are not related with the CN and SN symmetry. Then that ligands are diastereotopic ligands. I'm taken here H and H, here H, HA, HB. These two are not related with any CN and SN symmetry. Therefore, these two hydrogens are diastereotopic hydrogens. And next one is substitution criteria. Substitution criteria. If the selected homomorphic ligands are substituted with a different group, the resulting products are diastereomers, then that products are diastereotopic ligands. Here I am taking same example I am taken here. HA, HB, and H. Here HA is substituted with methyl, hydrogen. HB substituted with methyl. So this is a cis compound and this is trans compound. Okay, cis and trans are diastereomers. Therefore, these two hydrogens are diastereotopic hydrogen. That means these two ligands are diastereotopic ligands. Last one is diastereotopic phases. Last one is diastereotopic phases. So that means again two is there. One is symmetry criteria. That means the selected phases are which are not related with the CN and SN symmetry, not related with CN and SN symmetry. Then that phases are dash stereotopic phases. I'm taking here one example. So this phase is not related with the CNS symmetry. Therefore, that phase are come under the dash stereotopic phases. This is symmetry criteria. Next one is addition criteria. That means the selected phase are substitution with a different group. If the resulting products are dash stereomers, then that product the phases are dash stereotopic phases. Here I am taking this is a compound. Same example I am taking. Okay, phase F1 and F2. Substitution from F1 like this. Bromine, here bromine, OH, hydrogen, methyl. Okay, if substitution with from F2 like this, phenyl, bromine, OH, bromine, H and methyl. These two are erythrothio. This is erythro compound and this is trio compound. These two, erythro and trio, are the dash stereomers. Therefore, these phases are dash stereotopic phases. So, like this, we are decided that the phases are addition either belong to enantiomer, dash stereomer, homomorphic. Okay, based on addition and symmetry or substitution and symmetry criteria. Next one is prochiral center. Prochiral center. Any center of molecule on substitution or addition, if the produces product, the resulting products are chiral stereoisomers, then that center is called prochiral center. Okay, I am taking one example here. This H1 and H2. H1 is substitution with bromine, OH, methyl, HBr, and H2 is substitution with bromine, like this. Okay, any center of molecule on substitution or addition, if the products are chiral stereoisomers as a product, that center of molecule is called prochiral center. Okay, when these two subunit of molecules are substitution with a different group, the resulting products are chiral stereoisomers. Therefore, this center is called prochiral center. This center is called prochiral center, and this process is called prochirality. This process is called prochirality. Okay, and next one is important one is nomenclature for stereoheterotopic ligands. Nomenclature for stereoheterotopic ligands. Very, very important. Nomenclature for very important. Nomenclature for stereoheterotopic ligands. That is a pro-R and pro-S. Pro-R and pro-S. Okay. First one, Hansen's method. First one is Hansen's method. In this Hansen's method, that 4 or 5 points are there, very important for identify that ligand is pro-R or pro-S. Okay. So first point is project the molecule prochiral center as a cross formula. Project the prochiral center as a cross formula. Second one is label the paired ligands. Label the paired ligands and replace paired ligand one at a time by its heavier isotope. Find out the hypothetical priority of the ligands. Assign pro-R and pro-S symbol to the ligand. Okay, I'm taking this example here. In this example, what is the first point? Project the prochiral as a cross formula. This molecule I am representing in Fisher projection cross formula, and label the paired ligands. Here two hydrogens are there. I am labeling it with one hydrogen as a HA, another hydrogen as a HB, and replace paired ligand one at time by its heavier isotope. So first HA here, HA I am replaced by its heavier isotope is deuterium. HA is replaced by heavier isotope is deuterium. Okay, I am replacing HA with deuterium. So then give priority according to RS nomenclature. Here 1, 2, 3, and it is anti-clockwise. Anti-clockwise means anti-clockwise, but the fourth priority is anti-clockwise. But fourth priority is in what vertical, and fourth priority is on horizontal. Fourth priority is on horizontal. Therefore, the nomenclature is pro-R. HA is the pro-R. This is R. Therefore, that HA is the pro-R. Again here, HB is I am replaced with heavier isotope. HB is replaced with heavier isotope and given now RS nomenclature direction. So it is a clockwise, but fourth priority is on horizontal. Therefore, it is a S. Therefore, the HB is a pro S. Is the symbol for HB is pro S. Is like this. We can giving the nomenclature for stereotropic ligands as a pro R and pro S. Next one is next method is Nasi-Puri method. Next method is Nasi-Puri method. So next one is Nasi-Puri method. If the high ranking unpaired ligand top and low ranking unpaired ligand at bottom of vertical axis, the paired ligands on horizontal lines. Okay, like this. What is if high ranking unpaired ligand top, high priority unpaired ligand is top, low ranking unpaired ligand is bottom on vertical axis, the paired ligands are horizontal. The paired ligands are horizontal. Use that top right naming when the higher ranking unpaired ligand is at the top of vertical axis and the paired ligand on the right side of the horizontal axis is pro R. So top right, one use it. Okay, use top right method. Top right. If that unpaired ligand is first priority unpaired ligand is top and low ranking unpaired ligand is bottom side, and our paired ligands are vertical. Paired ligands are vertical. Use first one is top right. First top right side and paired ligand is pro R, left side paired ligand is pro S. Simple it is. Next one is bottom left. Okay, next bottom left. If high priority is ligand is bottom and low priority ligand is low priority unpaired ligand is upside, then left side is pro R. Bottom left nomenclature we can use like this. Nasi-Puri method is there. Okay, so this is a topic we are discussing, and topicity and prochirality. Okay, continuation classes next 12 to 1:30 also I am continue this class. Okay, that is unit 17 we will continue 12:30 to 12 to 1:30 class. Thank you.